Good day to all of you. In the previous several sessions, we had spent adequate time on the components that are going into the power converters, and these were namely switches, followed by energy storage elements, and these energy storage elements were inductors, capacitors, and transformers. So, we had spent enough time on understanding the characteristics of switches, operation of the switches, then the energy storage elements, inductors, capacitors, and then transformers for transforming the power. In all these cases, we had spent adequate time to understand their basic characteristics. What we are going to do in this lecture is to spend adequate time on the interconnection of these various elements. These elements will be interconnected in such a way that we carry out the power conversion function satisfactorily. The switch that we had looked at was an on-off switch, but for the purpose of interconnecting them in a circuit, we tried to understand this circuit or understand a particular form of switch, which is a single pole double throw switch, and then an energy storage element inductor and an energy storage element capacitor. This particular configuration of a switch is called a single pole and a double throw switch. There are two throws in this switch, T1 and T2, and there is a single pole in the switch which is denoted by P. A very simple power converter will consist of one switch and at least one energy storage element. So, we might put together for the purpose of our simple understanding a primitive converter. What we are going to now study in this session is about a primitive converter, and this converter will consist of a single switch and one inductor. How we connect them together? Following certain principles on circuit theory in order to carry out the power conversion function efficiently is what we are going to do in this lecture. The switch and the storage elements are going to be connected as part of a power converter in order to transfer power from a source. The source could be a voltage source or the source could be a current source. So, from the source we are going to draw this power, draw the power through switches and storage elements and transfer it to the load, which is a resistive load in this particular case. So, while interconnecting the sources to the switch and the energy storage element and eventually to transfer the power to the resistive load, there are certain conditions which have to be honored. There are certain circuit principles which have to be followed, and those are the things that we will see first. The interconnection rules are as follows. If you have a source, a current source or a voltage source, they may not be overloaded. This is one of the first principles that we have to honor. The voltage source or the current source may not be overloaded. In turn, this will translate into voltage sources are not to be short circuited, in which case infinite current will be drawn out of that, which can damage the voltage source. In the same way, a current source is not to be open circuited, in which case the voltage across the current source will go to infinity and this will result in overloading of the current source. So, from the point of view of the sources, there are two conditions that we have to ensure, and these conditions are: the voltage sources are not to be short circuited and the current sources are not to be open circuited. Then we have conservation of energy, which is the bedrock of all engineering discipline, and the conservation of energy states that energy is to be conserved and energy continuously varies, energy cannot be interrupted. The consequence of this conservation of energy is that if a current is flowing in an inductive circuit, if we have current flowing in an inductive circuit, that cannot be interrupted instantaneously. Such an interruption of inductor current will give rise to collapsing the energy to 0, and this is not to be done. This will give rise to over voltages in the system. And the dual of this is that the voltage across the capacitor is an energy variable. The capacitor has an energy, stored energy of half CV square, and if the capacitor voltage is interrupted or short circuited instantaneously, the capacitor energy is also killed instantaneously, and these are not to be done. So, the two interconnection rules are here, that the source may not be overloaded, which can be translated into no short circuiting of the voltage sources, no open circuit of the current sources, and then the energy has to be conserved, which indicates that the inductor current may not be interrupted and the capacitor voltage should not be shorted. If we follow these rules, then it is possible to translate these rules into certain simpler conditions for the switches and the energy storage elements that we are using. The switch is such that the pole may be connected to T1 for some time, or the pole may be connected to T2 for some time. So, the consequence is that the potential at point T1 and potential at point P may be the same. So, if a switch has to be used along with a voltage source, it is very clear that we cannot connect a voltage source between T1 and P. Voltage sources may not be connected across PT1 or across PT2, because in such a case, when P is connected to T1 or when P is connected to T2, the voltage source will be short circuited, and that is not to be done. In the same way, this should be current sources here. What you see here, no short circuit of voltage sources. In the same way, capacitors may not be connected across PT1 and PT2. The same argument holds. If P is connected to T1 and we have a capacitor between P and T1, the capacitor voltage is short circuited, and the same is true for P and T2. So, these are the two rules as far as the voltage source or capacitors are connected. Voltage sources cannot be connected between P and T1, voltage sources cannot be connected between P and T2, and so also capacitor cannot be connected between T1 and P, capacitor cannot be connected between T2 and P. Okay. This is the first interconnection rule. The second one is a dual of this. Current sources may not be connected in series with T1 or T2. If we have an inductor in series with T1, when the switch is thrown from PT1 to PT2, the current in the inductor is interrupted, and that will give rise to the inductor energy being disrupted. So, we would say that current source may not be connected in series with T1 and or T2. And there is a similar condition that current sources may not be open circuited. In the same way, if we have a current source, it cannot be connected in series with T1 or in series with T2, and the interconnection rules as far as inductor or current source is concerned is that they may not be connected in series with T1 or in series with T2, but they may be connected in the main path, because whenever the switch is connected from switched from PT1 to PT2, we may have one circuit carrying current before the transfer of the switch, and the current will transfer to some other circuit after the switch is shifted from T1 to T2, and that is acceptable, and so any current source may be connected in series with P. So, these are the interconnection rules, and if we follow these rules, there are two possible switch storage cell configurations. What you see here, a switch plus storage cell can be achieved in two different ways. We might use an inductor in series with the pole of the switch, or we might use a capacitor across T1 and T2, and this condition ensures that the current in the inductor is never interrupted, it is always in the main circuit, and the voltage across the capacitor is never shorted, because the switch will be either at T1 or T2, but never connected between T1 and T2. So, these two circuit configurations are acceptable switch storage cells, and one is the dual of the other, and in this particular lecture what we will notice or what we will follow will be application of this storage cell, and then later on we will see that a dual to what we are studying exists, and a similar kind of analysis and operation can be followed for the other switch plus energy storage combination as well. This converter, a primitive power converter, we might call this as a primitive voltage to current converter, is the starting point of all our power converter circuit topologies. The switch plus the inductor cell that we had seen just before is now connected between a source, a voltage source on the left hand side, what you see here, a voltage source on the left hand side, and the load on the right hand side. This being a DC power to DC power converter, the load invariably will consist of resistive load. We have a switch which has a single pole, and the pole has an inductor connected in series with that. The other end of the inductor is connected to one end of the load. The return wire of the load is connected back to T2 and then back to the source voltage Vg, and the positive pole of the Vg is connected to the pole T1 of the switch, and the switch is capable of being connected either to T1 between P and T1 or between P and T2. These are the two possible switch positions, and we might say that the power converter is taking power from the source Vg and delivering it to the load at this end at a voltage of V0. The load current may be defined as I0, and the source average current may be defined as Ig. So, this is the very primitive converter, and it is possible to understand many operations of the power converters, many analysis methods of the power converters, and many results that are very crucial in the study of power converters from this primitive converter, and later on expand on the same. Now, we will also define certain average quantities at the input side and certain average quantities on the output side. The source end is Vg, from where the power is taken, and the load end is V0. At the load end, power is delivered. The power is taken from a voltage source Vg through a current of Ig and delivered to a load at a voltage of V0 at a current of I0. These average quantities can be defined Vg and Ig at the source end and I0 and V0 at the load end. The operation of the switch and the converter is as follows. We consider one switching period as a duration of Ts. What we see here, a switching period may consist of a time duration of Ts, and in this Ts we will have two intervals, one called T on and the other called T off. So, every switching interval consists of a sub period of T on and a period of T off. During the on sub period, during the interval T on, the switch is connected between P T1. What you see here, the switch is connected between P and T1, and during the time T off, or it is known as the off interval, the switch is connected between P and T2. So, we might say that this end is T on and this end is T off. The switch has two positions, and in one switching period of Ts, 0 to Ts, the switch is on for a duration of T on connected between P T1, and it is off for a duration of T off where the switch is connected between P and T2. This is the operation of the switch, and on account of that, this converter will transfer energy from Vg to load at V0, and let us look at some of the operating conditions and operating performance in this. The dual to that is a single switch plus a capacitor configuration taking power from a current source Ig and delivering power to a load at a voltage of V0 and at a current of I0, and the elements used in the converter are the same single pole double throw switch, but with a capacitive energy storage element. Now, such a switch plus a capacitor cell is capable of taking energy from a current source and through the converter it can deliver to the load, which will also be resistive in this case. Here also it is possible to define average quantities at the input, which is Ig and Vg, and average quantities at the output, which are I0 and V0. So, let us look at how the performance measures for this converter are going to be specified and how these performance measures are going to be evaluated. The ideal performance measure is what we are interested in. So, during the ideal performance measure, we will consider every element in the converter to be ideal. All the switches, when they are on, will have 0 voltage drop across them, and when they are off, will have no current flowing through them, and the inductor will be a pure inductance with no resistance associated with that. So, we have only two elements in the power converter, switch and an inductor. The inductor is an ideal inductor, the switches are all ideal, and the operation of the switch is also following the ideal measures. That is, the time taken for the switch to shift from on state to off state is 0, and the power losses associated with conduction as well as switching are all 0. In such a situation, the performance measures are the following. If we have a power converter which is drawing power from Vg, what will be the output voltage, or what is the ratio V0 by Vg when the converter is operating under certain operating conditions. The first performance measure is the forward voltage conversion ratio. The forward voltage conversion ratio is the output voltage V0 divided by the input voltage Vg. How do we evaluate that? The next performance measure is the reverse current conversion ratio. This is the ratio of the average input current Ig divided by the average output current I0. So, this ratio also can be calculated if we understand the operation of the converter properly. The forward voltage conversion ratio is evaluated based on the principle that the average voltage across an inductor in one cycle is 0. What I have written here, the average voltage across the inductor L here over one cycle is 0. This statement is the same as saying that there is no DC voltage drop across an inductor. All of us know that the impedance of an inductor for DC is 0. So, whatever current is flowing across the inductor, if it is a DC current, the voltage drop across the inductor will be 0. The average voltage on one end of the inverter will be the same as the average voltage at the other end of the inductor. On an average, inductor does not support any voltage. All these are equivalent statements as the average voltage across an inductor in one cycle is 0. So, what we see here is that the switch is operating with a duty ratio with a switching period of 0 to Ts, and in that from 0 to T on, during the on state of the switch is connected from P to T1, and on account of that the voltage Vp, this is the pole voltage, is the same as the source voltage Vg. So, during the on time the pole voltage here is the same as the source voltage Vg, and during the second interval from T on instant to Ts, this duration is the off duration. During this entire off duration, the switch P is connected to T2, as a result of which the pole voltage Vp will be 0, because this is connected to ground. And what we see here is that in one cycle during the on period, the voltage across the inductor is Vg on one end and V naught on the other end, and during the off period of the converter, the voltage across the inductor is 0 on one end and V naught at the other end. The right hand side voltage on the inductor is always V naught, shown by the red color line here. So, from this waveform of the voltage across the inductor, it is possible for us to find out the forward voltage conversion ratio. From this, we can see that the inductor voltage is the same as Vp minus V naught. So, from the pole voltage, if I subtract V naught, the difference between them is the voltage across the inductor. So, during the on time, the voltage across the inductor is Vg minus V naught, and during the off time, the voltage across the inductor is 0 minus V naught, and the duration of off time is Ts minus T on, and the on time duration is T on. So, if I find out the average voltage across the inductor, it is Vg minus V naught into T on, the first half of the first sub period of the switching period, and then the second period is minus V naught into Ts minus T on, and this average voltage has to be 0 for an inductor. And if we expand this, this gives rise to the relationship of forward voltage conversion ratio V naught by Vg is the same as T on by Ts, and we give a name to that called duty ratio. D is the duty ratio, and it is the ratio of on duration 0 to T on divided by the total duration Ts. So, this is the first performance measure of a power converter, of any power converter. The first performance measure is the ratio of output voltage to input voltage. Under ideal condition, for this primitive converter, this is the same as the switch duty ratio. The second performance measure in any converter is the ratio of the average input current in relation to the average output current. The reverse current conversion ratio is the ratio of the average value of this Ig of t divided by the output current I naught. This ratio is called the reverse current conversion ratio, and this can be obtained by simply averaging the current waveform Ig of t. What I have shown here for one cycle, the average current of Ig of t is given by the red line Ig. This Ig of t, when the switch is on, it is the same as I naught, the current is flowing through the switch, and when the switch is off, the inductor current is freewheeling through Pt2, Ig of t is 0 during this interval. So, if we average this section I naught into T on is the same as Ig into Ts on averaging this, and we get the ratio of Ig divided by I naught is T on by Ts, which is also the same as the duty ratio. The forward voltage conversion ratio V naught by Vg was D. This is the reverse current transfer ratio Ig by I naught. This also happens to be D. This is obtained by simple geometrical averaging. We find that the ratio of V naught by Vg and Ig by I naught, both of them are D, okay, the duty ratio of the converter T on by Ts. If you invert this Ig by I naught as I naught by Ig and multiply by V naught by Vg, what we will get will be the total output power of the converter in relation to the input power of the converter. V naught by Vg multiplied by I naught by Ig is same as d into 1 by d equal to 1. So, what we notice is that the forward voltage ratio and reverse current ratio being same, when you multiply V naught I naught and then find the ratio of V naught I naught to Vg Ig, it is d into 1 by d, which is 1. This signifies that ideally the efficiency of a converter is unity. All the power that is drawn from the source is completely delivered to the load, and there are no losses in the switch or in the inductor. This is what we expected, because all the components that are used in the converter have no losses, and naturally therefore, all the power that comes out of the source has to be delivered to the load with no losses in the converter, and this is what we see as the efficiency of the ideal converter being unity. Okay. But there are several non-idealities in the converter. We had assumed that this converter has a current which is perfectly constant and an output voltage which is perfectly constant, and this Ig has an average value of capital Ig, and current power is drawn from the source Vg. But in a real converter, these ideal conditions of I naught being continuous constant and V naught being continuous and constant are not really true. They are different, and what we are going to do in the next few sections is how to find out this non-ideality. To what extent the converter current is not perfectly constant, to what extent it is different from the ideal condition. Okay, this is the first non-ideality in the converter, and this can be very easily found out by understanding that the current in an inductor is nothing but the integral of the voltage across the inductor. The inductor voltage is Vg minus V naught during the on period and minus V naught during the off period. This we have already seen when we evaluated the average voltage across the inductor being 0. So, this voltage is what is applied across the inductor as VL, and so the current through the inductor will be the integral of this voltage waveform. So, during the on period, current will keep increasing at a rate which is decided by Vg minus V naught divided by the value of the inductance, because L di by dt is voltage, and so the current during this interval will be the integral of the voltage across the inductor divided by L. Similarly, during the off period, negative voltage is applied across the inductor, and so the inductor current drops. The integral of this negative voltage is a ramp falling downwards, and under steady state condition, the rise in current will be the same as the fall in current, and so this current ripple during the on time, current ripple delta I naught, and the current ripple delta I naught during the off time, both will be equal. And this can be found out either from this end or from the off interval, and that is the change in current is the integral of this voltage, which is nothing but the area under this curve, which is V naught into Ts minus T on divided by L. That will be delta I naught, and that is given here as V naught by L multiplied by 1 minus d into Ts. The integral of the voltage across the inductor is used in order to evaluate delta I naught. Now, this can be put in a normalized form, because delta I naught by itself may not be of great use to us, but we might try to change or get a ratio delta I naught as a function of I naught. What is the ratio of the peak to peak ripple in relation to the average current can be found out from here. The ratio of delta I naught in relation to the average current, delta I naught by I naught. This is the same result as before divided by I naught, and V naught by I naught is nothing but the load resistance R. So, we replace this quantity by R and write it in a form which is 1 minus d Ts divided by L by R. This is the ratio of switching period divided by the time constant of the output circuit L and R time constant multiplied by 1 minus D. Okay. So, if the non-ideal condition of ripple current has to be very low, then we can say that this non-ideality, which is delta I naught by I naught, which is 1 minus d Ts by L by R, has to be very much less than 1, or we can alternately say that the switching period Ts has to be very much less compared to the circuit time constant L by R. This is one of the conditions for the non-ideality to be negligible, or for the converter to perform as close to the ideal as possible. The other non-ideality in the converter is that the switch T1P and T2P do not have 0 voltage across them. When current is flowing through the switch T1 to P, there is a small voltage drop across the switch, and similarly when the current is flowing from T2 to P, there is a voltage drop across the switch. This depends on the type of switch that we use. In a real converter, these switches T1P and T2P are realized by a transistor switch or a MOSFET switch, what you see here, and a diode. The T1P is realized by an active switch, which can be a bipolar junction transistor or a MOSFET or an IGBT, and the switch T2P is a passive switch. It can be a diode for this direction of current I naught. Now, while current is flowing through the transistor, there could be a voltage drop of Vt. We call the voltage drop in the transistor while it is on as Vt, and similarly the voltage drop across the diode when the diode is conducting is defined by Vd. So, with these definitions, it is possible to find out how the voltage conversion ratio is going to be different when these non-idealities are introduced. The switch voltage is Vt, the diode voltage is Vd. So, in the voltage across the inductor now, we will find that during the on period, the inductor voltage is Vg minus Vt minus V naught. V naught is the average output voltage, and on the freewheeling side, the voltage is diode drop minus V naught. Diode drop is in the negative direction. So, effectively, the inductor on state voltage is Vg minus Vt minus V naught. Off state voltage is minus Vd minus V naught, and with this we can recalculate the volt second balance on the inductor. This volt second balance is nothing but the average voltage across the inductor in one cycle. That is also referred to as volt second balance, and when it is evaluated, it is Vg minus Vt minus V naught, which is this area of this hatched region, this multiplied by T on. Similarly, this during the off period minus Vd minus V naught multiplied by the off period, and if the total volt second is made equated to 0, then we get a ratio of this output voltage as d times Vg, which is the same as the original ideal condition. Ideally, when the switches were not dropping any voltage, output voltage was d times Vg. But in addition, now we have a correction factor. This correction factor, as you can see, is less than 1. It is less than 1 by 2 ratios. One ratio is the transistor voltage divided by the source voltage, and another ratio is 1 minus d times the diode voltage divided by the ideal output voltage. D times Vg is the ideal output voltage. So, if we put these, if we keep these ratios in mind, we will find that the output voltage will differ by the ideal output voltage by a factor which will be less than 1. So, this is the correction factor on the ideal conversion factor. V naught by Vg is now D, which is the ideal gain multiplied by a correction factor. This correction factor is close to 1, but it is less than 1 by these ratios: transistor voltage by source voltage, diode voltage divided by the output voltage. Okay. Another interesting thing is, even though the switches are replaced by real switches with non-ideality, if we evaluate the average input current Ig of t, what we see here is the average input current Ig of t, if we evaluate that, there is absolutely no change in that. During t on, the current through the switch is I naught, and during the off period current through the switch is 0, and when you average it, we still get the same ratio. Ig by I naught is the same as T on by Ts, which is a duty ratio. The important point to note is here is that the switch non-ideality has not affected the reverse current transfer ratio. It affected the forward voltage transfer ratio, but it did not affect the reverse current transfer ratio. The reason is that all the switch non-idealities that we see here are series non-idealities, and series non-idealities normally do not affect current ratios. This you can check as a homework exercise, that these series non-idealities do not affect the current transfer ratio, but they do affect the voltage conversion ratio. The interesting part is that now the product of the voltage conversion ratio and current conversion ratio in the ideal converter was 1, which was the efficiency of the converter. In the non-ideal converter, I naught by Ig is 1 by D, V naught by Vg is D multiplied by this quantity. So, when you multiply these things together, the efficiency of the converter is the same as the correction factor that we found in the voltage conversion ratio, or the power conversion efficiency is less than 1. There are some losses in the converter, and this loss is seen by this number efficiency, which is being less than 1. It is less than 1 by 2 ratios. First ratio is the input ratio, which is the transistor drop in comparison with the source voltage, and the second ratio is the diode drop in comparison with the ideal output voltage. So, by these two ratios, the efficiency is less than 1, and to that extent there will be losses inside the converter. Now, we can look at one more type of non-ideality in the converter other than the switch drops, the non-ideality in the source and the inductor. The source can have a resistor as shown here Rs, and the inductor can have similarly a resistance of the winding RL. So, these quantities also give rise to some difference in the voltage transfer ratio. Because these are series non-idealities, they do not affect the current transfer ratios. Current transfer ratio will continue to be as before, but let us look at the voltage transfer ratio. So, now the voltage across the inductor is now the pole voltage minus the output voltage V naught. V naught is shown here by the red line, but the pole voltage now consists of source voltage minus the inductor current multiplied by Rs multiplied by RL, I naught into Rs plus RL, and while freewheeling the drop is having a drop of minus I naught RL, and so we notice that the voltage across the inductor during on time has a non-ideality minus I naught Rs plus RL, and during the freewheeling time has a non-ideality of I naught into RL, and if we combine these things and find out the volt second balance, this V naught by Vg, applying this average voltage across the inductor being 0, V naught by Vg now has the ideal ratio D multiplied by a correction factor. Here also the correction factor is less than 1. It is the load resistance divided by load resistance plus duty ratio times source resistance plus the inductor resistance, and this number will be close to 1, but less than 1, and that is what we notice here. And just as before, the current conversion ratio is not affected by the presence of Rs or RL, because these are all series non-idealities. When we evaluate the average current, it continues to be as before, and so the ratio of Ig by I naught is still the same as duty ratio, and the consequence of that is the efficiency of this converter is the same as the correction factor in the voltage conversion ratio, 1 by 1 plus this Rs into D by R plus RL by R. These ratios are small numbers. So, in the denominator you will have 1 by 1 plus a small quantity. So, there will be some loss, but the overall efficiency will be close to, in typical converters, the efficiency will be better than 90%. and these losses are because of the parasitic resistances. Now, when both switch, source and inductor, all the non-idealities exist together, it is possible to work out all the average voltage across the inductor expressions, and it is possible to find out the efficiency to consist of two different correction factors, one because of the switch non-idealities and the other because of the source and inductor non-idealities, 1 minus Vt by Vg minus 1 minus dVd by dVg. This dVg is the ideal output voltage, and similarly in the denominator there are a few ratios here, source resistance by load resistance and inductor resistance by load resistance. This correction factor or the efficiency factor will be very close to 1 if all these non-idealities are quite small. So, in a converter, if we want good efficiency, these are the guidelines. The device voltage drop must be very less compared to the source voltage, and the freewheeling diode voltage drop has to be very much less compared to the output voltage. The source resistance must be small compared to load resistance, and load resistance must be small compared to the inductor resistance must be small compared to load resistance. If these guidelines are followed, then efficiency will be normally close to 1. Now, we have another non-ideality which we have not seen up to now, and that is the non-ideality related to the output voltage. We had assumed in the analysis up to now that the output voltage is a perfectly constant voltage V naught. But in reality, this output voltage also will have a non-ideality, and this non-ideality is the variation in the voltage in V naught. V naught will not be perfectly constant, but it will be varying around a DC voltage, and how much of ripple voltage is present on V naught is the non-ideality related to the output voltage. So, we had seen up to now several performance measures. One of them is V naught by Vg, called the forward voltage gain. The second one was Ig by I naught, called the reverse current gain. We started with an ideal converter. We saw that these gains, the voltage transfer gain has or is affected by the non-idealities in the switch, non-idealities in the source and so on. And we also saw that the inductor current is not perfectly constant. It has a ripple delta I naught, and this delta I naught by I naught is related to the switching period divided by R by L time constant of the converter. And if that has to be small, we said that switching period has to be very small compared to the L by R time constant of the converter. Now, we have the next non-ideality which is relating to the output voltage. Output voltage ripple is a function of the load. Okay. Typically, the load will be supported by a capacitor. What comes out of this I naught, if it is directly connected to R, then delta I naught by I naught and delta V naught by V naught will be the same. The current ripple and voltage ripple will be the same if it is a simple resistor. But in most converters, in order to reduce the overall energy storage requirement, the load will be supported by a capacitor as shown here. A capacitive support is provided to the load. So, in such a case, how do we find out what is the voltage ripple on V naught on account of the performance that is happening in the converter? Okay. What we notice is that this current in the inductor has the ideal value I naught plus a ripple delta I naught, and this we had already evaluated to be a function of the switching period, inductance, duty ratio and so on, Vg and so on. Now, the next non-ideality we are looking is whether this output voltage V naught, what is the amount of variations or the ripples that are present on that. So, what we want to now evaluate is the output voltage ripple delta V naught, and if possible, what are the measures in order to make it as small as possible. We see that from the previous one, it is I naught plus delta I naught is the current coming out of the converter, and out of that this delta I naught is a ripple current or the high frequency current, I naught is the DC current. So, we may safely assume that the DC current will flow through R and the AC current or the high frequency variation current will go through the capacitance, and so any change in the capacitance voltage will be because of the of the current ripple that is passing through the capacitor. We know that in a capacitor, the current is C times dV by dt. So, this can be written, if all these are simple triangular currents, we can write this as the integral of that divided by C will be delta V. So, the charge that is flowing into the capacitor, which is the area of this triangle that we see here, is what is responsible for the capacitor exhibiting a voltage ripple delta V naught. Delta I naught we had seen earlier is V naught by L into off period, and off period is 1 minus d times Ts. So, if the ripple is known as V naught by L into 1 minus d Ts, the area of this triangle is the charge that is transferred to the capacitor during the minimum to the maximum voltage, and we can write the delta V naught to be delta I naught by 2 is the height of this triangle, and 1/2 is for the area of the triangle, and the duration from here to here is, from what you see here, the duration from here to here is Ts by 2, and this entire charge divided by C is delta V naught. So, now we can evaluate delta I naught as V naught by L 1 minus d Ts. We have already seen this. Delta V naught is as per that the area of the total charge divided by C, and that works out to be V naught 1 minus d Ts square divided by 8 Lc. And if we take the ratio as of importance to us, voltage ripple delta V naught by V naught, it is 1 minus d multiplied by square of the switching period divided by 8 times the Lc product. This quantity gives us a guideline for low output ripple. If delta V naught by V naught has to be very small, then the right hand side expression has to be small, or we might say that the switching period Ts has to be very much less than the natural frequency, or we might say Ts must be very much less compared to 1 by root Lc. This is the natural frequency of the converter, what is on the right hand side. What is on the left hand side is the switching period of the converter, and if this inequality is satisfied, the converter will have very low voltage ripple. Okay. So, in effect, now if we try to summarize how we found out the steady state performance of the converter, there were several steps that we went through. Let us see those steps. The first measure that we defined was the voltage gain V naught by Vg. The second measure was the current gain I naught by Ig. Then we evaluated the ripple on the inductor current delta I naught, and we said that it has to be very much small compared to the DC current that is flowing in the inductor. That gave rise to some guidelines. Similarly, the voltage ripple also we could evaluate as a ratio of high frequency ripple voltage divided by the DC output voltage. The DC output voltage is the useful voltage, and the ripple voltage is the non-ideality on that. DC current is the useful current, delta I naught is the non-ideality on that. V naught by Vg tells us the control performance, how we are able to control the output voltage from the input voltage Vg. This current gain tells us how the load current is reflected on the source by the ratio I naught by Ig. And we saw that there were, under ideal conditions, all these numbers had certain performance numbers, and then there were several non-idealities. The switch itself had certain drop in voltage during conduction, and the source had a resistance, the storage element inductor had a resistance. So, when these are present, how do we account for all these quantities with the non-idealities present, and finally the efficiency. So, the method that we had followed is voltage gain was obtained by the inductor volt second balance. That is the step What we will notice in the converter circuits that we will be studying in the next session and so on, is that this sequence is the same. We use volt second balance in the inductor to find out the ideal V naught by Vg. Then the current averaging is worked out to find out the ideal ratio of I naught by Ig. Then the inductor volt second in every sub period is calculated to find out what is the ripple in the inductor current, and then as a ratio with the average current, it is possible to get a guideline on how to make sure that this non-ideality is as small as we want. Similarly, the next step is the capacitor voltage in the sub period, and this is evaluated based on the capacitor charge, how much charge is transferred from the circuit to the capacitor in every sub period, and that charge is responsible for delta V naught. Compare it with V naught to find out the guideline on the ratio of delta V naught to V naught, and if we carry out the inductor volt second balance with the non-idealities, it is possible to find out the efficiency of the converter. The non-idealities of the switch, voltage drops, the non-ideality of the source resistance, similarly the inductor resistance, all of them give rise to some additional losses. In the ideal converter, if the switch is ideal, if the inductor is ideal, then we see that there are no losses in the converter. But when we introduce the non-ideality, it is possible to find out the ratio of V naught by Vg, I naught by Ig, applying the inductor volt second balance as well as current averaging. And once these numbers are found out, the product of these two will give us the efficiency, V naught into I naught divided by Vg into Ig. We had seen that all non-idealities which are of series nature, series non-ideality, like the switch voltage drop, the diode voltage drop, the source resistance, the in the previous one we had seen the non-ideality in the switch, which is a voltage drop, in the source, which is a resistance, in the inductor, which is a resistance. All these non-idealities we saw that did not affect the current gain, because all of them are series non-idealities, and series non-idealities do not affect the current ratios in a circuit. And all these non-idealities, because they give rise to a voltage drop in each one of those loops they are associated with, the voltage gain is affected by them, and the ratio of V naught I naught Vg Ig is what is efficiency, and one ratio I naught by Ig is not affected by any of the non-idealities. V naught by Vg only is affected by the non-idealities. So, the efficiency will directly be the correction factor in V naught by Vg. That is also something we had seen. So, in the converters that we are going to study hereafter in the next few sessions will be extensions of this primitive converter. In the primitive converter, we have learnt several interesting things. We had understood the ideal performance functions, steady state performance functions. We had understood the non-idealities associated with the inductor current. Inductor current is associated with the stored energy in the inductor. Capacitor voltage is associated with the stored energy in the capacitor, and the non-idealities in the inductor current and capacitor voltage are the ripple associated with the respective current and voltages, and the product of V naught by Vg multiplied by I naught by Ig is the efficiency. So, in effect, the steady state performance are just these 5 functions. The ideal functions are very easy to evaluate. In the non-ideal case also, all that we use is only the inductor volt second balance. To find out the current ripple, we integrate the voltage across the inductor in every sub period. To find out the voltage ripple, we integrate the current through the capacitor in every sub period. And so, these 5 performance functions are the important ones for every converter, and all these functions will be evaluated in a very similar way in every one of those converters. What we will see now is that how the circuit that we had seen can be modified to obtain several other power converters. What you see in this picture is the equivalent circuit of several transistor amplifiers. A transistor has a base, emitter and a collector. The base current multiplied beta times is the collector current. So, it is possible to use this amplifier, this transistor as an amplifier in several ways. You can use it in what is known as a common collector amplifier, where the input is between base and collector and output is between emitter and collector. This is a common collector amplifier. In the same way, we could use it as a common base amplifier, where the input is given between collector and base and output is taken from emitter and base circuit. This is a common emitter amplifier. This is normally the most common arrangement for transistor amplifiers. So, common emitter amplifier, the input is in the base emitter circuit and the output is in the collector emitter circuit. It is very interesting that in a very similar way, we have three possible ways of connecting the primitive switch inductor cell. The switch and inductor, what we had analyzed up to now, but inductor at the front and switch at the back feeding to the load is the next configuration. Switch, inductor in the middle and switch connected both to the input and the output is the third configuration. Normally, these three circuits are known as buck converter, the boost converter, and the buck boost converter in the power converter topologies, in the power converter terminologies. And you will find that these are the basic circuits which have come from the same primitive cell. The switch plus an inductor connected in this way is what we had analyzed up to now, and the switch and the inductor connected in a different way, where the inductor is connected to the source and then the capacitor, the switch is connected to the load end, is called the boost converter, the second one. And the third one is where the switch T1 is connected to the source, T2 is connected to the load and the inductor is in the common circuit. These three variants are the basic converters, and in the next lecture we will spend some more time on the other two converters, evaluating many of these performance functions of these converters. So, we will stop with this. The next lecture will be on the buck boost and the buck boost power converters. Thank you.